talked about systems thinking. Okay, what about systems thinking? Yes, sir.
Oh, we learned some benefits.
What's that?
We learned some benefits.
Okay. All right. Okay. A framework, a structure, develop tool sets, all that good stuff. Hopefully this thing's gonna turn on. There it goes. We talked about right brain, left brain, creative versus very organized. All right, and how most of us are a little heavier on one side than the other. All right. How many people feel that they're more creative than structured? A couple of you. Okay. How many people feel the opposite? Who feels like they're just perfectly balanced? Okay. So no matter what your bent is, you can, with effort, change that. So throughout my entire life, I have been very much an organized person, a person who makes lists, and I'm always looking at what do I need to do next, what are the steps that I need to do to get there. It's served me very well in my life. When I retired from the Army in 2015, I thought, I want to do something different. I want to try to be creative. All right, because, well, y'all seen my stick figures, right? They're kind of ugly. All right, but I thought, I've never really done anything that I consider to be creative in my life, and so I thought I want to try something different. And so I thought about jewelry making, specifically wire wrap making, and I started watching some YouTube videos and doing some different things, and really made some exquisite works, and I was just completely surprised that, wow, all this time I've had this latent skill that I didn't even know was there because I never really gave it an opportunity. All right, so the point of this little thing is that, you may be heavily bent on one way, but that doesn't mean that you don't have any artistic ability. I still can't draw very well, all right, but I can do some different things. I also do some blacksmithing, forging type stuff, and when it comes time to machine stuff and do all that, I'm very creative, and I've made some very exquisite pieces. All right, so you can train the other side of your brain to do more than what it has been doing. All right, so we talked about the left and the right. All right, so I think this is where we left off. All right, and so the y times 9. Has anybody ever heard of this before? Okay. And this is up on the thing. All right. So basically, what this is an opportunity for you to expand your horizons, a chance for you to look at different perspectives, right? And so what they're saying is, look at it as you would normally look at it, right? And you're going to form some basic assumptions from that. All right, and then what we're going to do is we're going to ask 3 why questions from each of these perspectives: leaders, peers, team members, or subordinates. All right, so what does that do for us? Taylor, what do you think that does for us?
Gives you like a broader understanding of things.
Yeah, it opens up. If I'm asking from somebody who works for me, and if I'm asking a question of why from their perspective, or even how, all right, it makes me think about what is their perspective? How is that different from mine, and why is it different from mine, and is it important? All right, and it probably is. It also helps us to look a side up, because also want to look at the leader's perspective. All right. How many people have held a job somewhere before? Most of you, great. Okay. Have you ever had that where management pushes down a decision and you're just like, why? This is stupid. All right. Well, we're all doing it right now, right? We're all wearing these masks, which, you know, we all know that. Okay, so using this y times y, or y times 9, allows us to step out of our own shoes, all right, and look at things from different perspectives to gain a little better understanding of what's going on. All right. Now, if I just step back and I say, from the supervisor view, why, I may not have the perspective to do it. I may actually have to go to that supervisor to say, hey, help me understand why. Okay, is this making sense to everybody? All right, so the Army uses this a lot. And so in the Army, and actually in the military overall, all branches do this. All right, so you enlist and you learn a particular job, right? That's what you do. And so you're a private E1, private E2, private first class, all right? And so as you learn that job, you become the subject matter expert, all right? Now, what the Army says is that once you learn that job, you really need to learn a job ahead of you. You need to learn your supervisor's job. Why would we need to do that?
So that when your supervisor, theoretically, I guess, when your supervisor takes their supervisor's job, you can move up and take the place of your supervisor.
Right, you've already got an idea of what it is that they do. You know what you do, you know what you do very well. But now you're starting to see some of this other perspective of what they're doing, okay? So, it's even better than that, because as you move up through the ranks, you're expected to know your job. You're supposed to be the subject matter expert. You're supposed to know your supervisor's job well enough that you can step in and fill their role if need be. All right? And in the military, that's really important, because what happens to leaders? They get killed. And now somebody's got to do the job quickly. All right? But also, I need to know 2 positions below me. So those positions that I've already done, I still have to maintain competence in those. All right? This is a really good model for developing leaders that have been through the structure, and they know the jobs below them, they know what they're supposed to be doing, and they have a really good idea of what the person above them does. All right? 1 up, 2 down is what they call it. So, it's the same thing. Right? By asking those questions, it allows us to see from a perspective outside of what we would normally see. And that's really what we're trying to do, is we're trying to understand things from a lot of different perspectives. All right, we can go back to this. So, no, we're not going to do that. We're going to do something. All right. We'll just join up the transition here. There's actually a couple slides hidden. So we use patterns and trends to detect problems and fix them. All right. Somebody look at this and tell me what you're seeing. Somebody I haven't called on. Yes, sir.
Inconsistent goes up and down over years.
Okay. What is it that we're looking at? It's data for what?
The number of sunspots.
The number of sunspot occurrences. All right. So, what's the blue? Okay. What's the red? It's basically an average, right? They've averaged out the monthly readings. All right. So, do we see a recurring pattern? All right. Why is any of this important? So you as a student, does this slide have anything to do with you? Do you have any concern with this slide? Yes.
Well, don't sunspots affect like satellites, so then like your Wi-Fi could be spotty or something like that?
Okay. Yes. So what happens when sunspots happen? Yes.
systems we built are disrupted?
Right, a lot of our communication systems, GPS is disrupted, Wi-Fi is disrupted, and so cellular is disrupted. What would you guys do if your cell phones didn't work? All right. So, what do we see? What is this pattern showing us?
That like roughly every 10 years they're going down in like a pretty consistent pattern.
Okay? Or the reverse of that is that every 10 years they're going up. But it also shows us that there's a cyclical thing to this. All right? So, this is an example of a piece of data that you might get out in the real world when you're working at your job. Okay? You get a graph, you get the blue graph. All right? And so, you say, oh, okay, that's cool. All right? So looking at all that information there, all right, gives us some different perspectives on this particular bit of information, all right? So how many people know that Taylor is getting ready to launch its 7th satellite? A couple of you, yeah. We're getting ready to launch our 7th satellite, all right? And one of the things that we're looking at is, well, what do we want to research? All right? And so the question is out there, okay, so what's going on? What should we research? What's been done? Is there anything that hasn't been done? Is there anything that's important to us that we want to answer questions about? All right. So if I were just to get this data and say, oh, okay, yeah, okay, so I see the sunspot activity, all right, I would probably still see, actually, when I get this data, it probably would just be a graph. It may not even have the graduations. So I've got to figure out, okay, what is this really telling me? All right. The red is me doing some statistical analysis on this and smoothing the curve out so that it makes a little more sense so I can see what the average is. All right. And then by adding in our headings, okay, I'm able to make more sense of this. So this communicates a whole lot of data. How many data sets does this communicate? I don't know, probably millions. All right, because this is from pre-1960 to 2000, probably 5. How many millions of readings have they taken? All right, so if I just got a download of that data, literally I probably couldn't fit all the paper in this room. All right, so we're compressing that data into a graph. All right, then we're taking that graph and we're making it more useful, more intuitive. We're making it so that other people can understand it, and even non-technical people can understand it. All right, so how many people are driving a newer car? Maybe within the last 5 or 6 years, maybe 10 years. None of you? Oh man, I'm sorry. How many people have external sensors on there like lane departure or accident avoidance, things like that, right? Okay, well, so I just bought a new truck, actually right a year ago. It's a 2020 Tacoma, all right? Previous to that, my newest car was a 2011, which I inherited from my mother, all right, which was a nice gift. It was free, all right. But so it has all kinds of systems. So it has the LDS lane departure. Is it LDS or LDA? I don't know. Lane departure assistant. I think that's what it is. It's got bright light detection, and it's got accident avoidance. Okay. So it's got a lot of different things that it does. So for the lane departure assistance, when it's on, it's actually looking for the center line of the road, and if I veer over it, it gives me a little warning. All right? Which sounds really cool, right? Let me tell you, on country roads, it really sucks because the thing is going off all the time. All right? One of the other systems that it has what did I say? Oh yeah, bright light detection. And I turned this on somehow. I don't know. I've had the truck for a year, and it has been. All of a sudden, it turned on. And so when I'm driving down the road and there's a car coming, the bright lights go off. Well, the first time it happened, I'm like, what was that? I'm like, oh great, I gotta take my car to get it serviced because there's something going on. Well, I drive by that car, bright lights came back on again. Okay. As you come up to a stop sign, your bright lights go off. It's literally driving me crazy. I'm like, what is going on with my truck? Well, then I figured out it's got this bright light detection system. All right. Accident avoidance. If I turn on the cruise control, I have 3 levels of control on how close I can get to a car that I'm following. All right. So I turn the cruise control on, and then if somebody pulls in front of me and they're moving slower than I am, it'll automatically apply the brakes. And consequently, if you go up a steep hill, it will apply the brakes. All right. So these are just 3 examples of systems that are placed in this car. All right. There's a lot more, but these are the ones that stand out. So what does it take, and we're going to break up into groups, what does it take, how many different systems have to work within these for it to happen and for it to be reliable? So let's get 3 groups. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2. If you're a 1 over here, if you're a 2 over there, if you're a 3 over there. So in your groups, we're going to do 1, 2, and 3. Talk about what systems are involved to make this happen. Pause this. Were we able, just in our groups, to break down these very complex systems and identify some major components of them? All right, and talk about rationally. We actually had some deductive reasoning going on over here to say, oh, on the lane departure assistance, it would just make sense that there's one on the left and one on the right, because if it's just in the center, well, you'd be all the way over in the other lane before it registered that you were out. Okay, so good. Decision making, we're going to talk about flow charts. All right, and so what we're looking at is, again, we're taking these really complex systems, we're breaking them down into bite-sized pieces that we can dissect, and we can look at one subsystem or even a subsystem of a subsystem, all right, and understand how it works. And through this this whole process, we can begin to understand and we can communicate to other people, even non-technical people, some very complex stuff so that they can understand it and make use of it. All right. So we're going to talk about the Fermi problem solving. Has anybody ever heard of Fermi before? Nobody? Catherine has?
I don't remember anything about it, but this sounds vaguely familiar.
Okay. All right. So how many piano tuners are there in Chicago? A few. Yes, there are a few. So let's ask some questions. How might I make some basic assumptions about this? How could I access readily available data and make some assumptions about how many piano tuners there are in Chicago? Same.
Population of Chicago.
Okay, that's probably a good start, right? Where do I get that?
Census.
Census Bureau. Okay, so that's a good start. Yes, sir.
if you find a population of like an area you know, and you know how many piano tuners are there, then you can multiply it to Chicago's.
Yes, we could do that. That's one way we can do it. So we can look at a known population and extrapolate. Right? So if we looked at, say we knew how many piano tuners were in Upland, all right, could we extrapolate that to Chicago?
Yeah.
Roughly. Now the question would be, are there more piano tuners per capita in Upland because we have the music school here and so forth and so on? I don't know. But we could make a rough guesstimate. All right. What else? Somebody else had their hand up. What you got?
How many pianos are there? That'd be a harder stat to find, but if you could either
Okay.
look around or talk to businesses that sell.
How many people play piano?
Yeah.
Okay. So there are a lot of different ways that we can do it. Go ahead, Sam.
You could try to find a piano tuners enthusiast group in Chicago and see if they collect their own.
Right. Well, there probably is an organization, right, that all piano tuners are a member of. Piano Tuners Anonymous, PTA. I don't know. But yeah, there probably is such a thing. All right. And so odds are that they probably have population density data and all that. All right. A lot of the stuff that we're trying to find is probably already there somewhere. All right. So this is one way that we can do this. So assume that an average family contains 4 members, so that the number of families in Chicago must be about 750,000. All right, and I don't know how old this is. If 1 in 5 families owns a piano, there will be 150,000 pianos in Chicago. If the average piano tuner serviced 4 pianos every day of the week for 5 days, resting on weekends, had a 2-week, he would service 1,000 pianos, 1 year, 50 weeks. All right, and so we wind up with 150 piano tuners. Okay. All right, Fermi. Enrico Fermi, an Italian physicist, architect of the nuclear age. Now is his name ringing a bell? Some of you not. Created the world's first nuclear reactor. All right, and so Fermi is known for this back of the envelope calculations or guesstimates, all right? And so for a lot of what I do, this is how things happen, is that 2 people are talking, they have an idea, and it gets sketched on the back of a napkin or a piece of paper, and then, we make some assumptions about that, and that begins the process of developing something, whatever it might be. So let's take another. How fast does the moon travel over the Earth? How might we estimate this without Googling how fast does the moon travel? I know Google is the answer. Does anybody have any ideas how we might solve this problem?
I mean, it'd kind of be a stretch, but if you figure out how long the shadow is on Earth, and then how fast it was moving, not how fast it was moving, but how much distance it covered in that time that it was on Earth.
Right, so if we have a defined geography, right?
Yeah.
If we have a defined geographic area and we're able to see how far it traveled over that, right, we can extrapolate that data. Very much like what we were talking about here. We have a known population and then we extrapolate that to a different population, okay? Basically the same idea, all right? And you're right on track. So what could we use to do this? And it's something that we use all the time and you probably don't think about. How many people have a family that lives out west? Okay, so when you're getting ready to call your family, what do you think about?
Time zones.
Time zones. How can that help us here? Yes, sir.
Limit the area we use.
What's that?
Limit the area we use.
Okay. So how many time zones are there across the U.S.? There are actually 4, but Mountain Time we're not going to talk about. So we got Eastern, we got Central, and then we got, what's this over here? Pacific Time. Then we got Mountain Time over here, is their own little thing. These people are different. I know somebody's going to tear me up on YouTube on that one. All right. How wide is the U.S.? How wide? Oh my goodness gracious, it's about 3,000 miles. Oh. Oh. I'm right, all your geography teachers. All right. Here they break it down. All right. Okay, well, first we have to understand that the moon is not moving, right? The earth is moving. U.S. about 3,000 miles, 3 time zones. So each time zone is roughly 1,000 miles. Okay. All right. Sun rises at about the same time in each time zone. So that's what do time zones do? So that when the sun is rising, sun is supposed to come up at 6 o'clock in the morning, right, in Eastern time. Well, Central Time people are an hour behind us, and at 6 o'clock in the morning, what's happening there? The sun is starting to rise, right? And then at 6 o'clock in Pacific Time, what? The sun is starting to rise over there. All right. So we have essentially about 1,000 miles an hour. All right. So we can take basic information and we can make some rough calculations to get us in the ballpark. Right? Now, I don't know what the actual speed is. Did anybody? Who's already Googled this? Kay, did you Google it yet?
No, sir. Should I continue?
I'm disappointed in you. You got a laptop right there. I'd have been like, it's 2,869 miles an hour. That's what I just said. I don't know what it is. What is it? You're letting me down, Kay.
What am I searching again?
How many miles does the Earth rotate in an hour?
1,000 miles.
All right. You got me crying, man. Oh my goodness. All right. So let's just stay in your groups and let's talk about, and on Friday we'll start off with talking about some of the ways that we might calculate these. All right. So in your groups, pick, say 3 of them, and talk about how you might make some Fermi calculations or Fermi guesses on these. And this is on Moodle. So you got 5 minutes and then we'll call it a day. So somebody in your group, remember what group you're in. This thing did not shut off on me today. Yay.
Seems easy.